In this session, we're going to examine increasing, decreasing, and constant intervals and extrema, and we're generally looking at or referring to graphs of functions in this context. Extrema, by the way, is just plural for extremum, and we're referring to, say, a local maximum or a local minimum. Sit tight, we'll get to it. Contrary to what I would usually do, I'm going to give you the example first to put everything into a context, and then I'll give you some formal definitions. This section is really about vocabulary and how things are written mathematically, more than the concepts, because the concepts I think are pretty accessible. Let's start by looking at a graph. Here we've got a wiggly graph that has a slope that's positive to the left of A. It's positive between B and C. It's positive between D and E. These values are referring to x-axis numbers. And it's positive when x is bigger than f. Those are intervals over which this function is increasing, getting bigger. Decreasing, that means getting smaller. We're looking at the interval from A to B, and then the interval from E to f. And then finally we have an interval over which the function is constant. That is, the function value doesn't change. And that would be the interval from C to D. Like I said, the concepts are very straightforward. As far as the definition, a little bit of mathematical notation. A function f is increasing on an interval I if f of b is greater than f of a whenever b is greater than a in the interval I. If normal people were talking, they would say y is getting bigger as x gets bigger. In other words, in the context of increasing and decreasing, what we're looking at is as we go along the x-axis from left to right, are the y values getting bigger or are they getting smaller? We have an analogous definition for a function decreasing on an interval. F is decreasing on an interval I if f of b is less than f of a whenever b is bigger than a in the interval. And again, if normal people were speaking, they would say y gets smaller as x gets bigger. And we can again see that in the graph above between, say for instance, E and F. As x is getting bigger along the x-axis, the function values are getting smaller and smaller. That is, they are decreasing. Finally, we have a definition for constant. A function f is constant on an interval I if f of b equals f of a for all values in the interval. And again, the picture there is where the graph flatlines between C and D. It's not getting bigger, it's not getting smaller, it's constant. So we've cleaned this up a little bit, same graph, and we're going to talk about how you would write down intervals over which a function is increasing, decreasing, and constant. As we said, a function is increasing essentially if it is getting bigger. So that's happening from negative infinity to a, from b to c, from d to e, and then from f to infinity. Now again, when we talk about increasing, it's as x goes from left to right. And so the fact that the function points down to infinity to the left of a makes no matter. What matters is, as you crawl on the x-axis from left to right, the function values are getting bigger. In this case, this function is decreasing on the interval from a to b, and then also from e to f. And finally, we have a constant interval from c to d, over which the function value does not change. To write this out, we would say, well, let's give this function a name. Let's call it g. And here we would say that g is increasing on the interval, or intervals, from negative infinity to a, square bracketed a, union with B to C, square bracket for both of those, union from D to E, and union from F to infinity. And notice we're using square brackets all around except for the endpoints that indicate infinity. G is decreasing on the intervals over which the function is getting smaller. So G is decreasing on the interval from A to B, and then also the interval from E to F. Finally, we would say that G is constant on the interval where it's flat, so the interval from C to D. Something that could be a hang-up is the fact that if you're paying attention, you can see that we're saying F is increasing at A. We're also saying F is decreasing at A. It all depends on how you're considering A. To the left of A, the function is increasing. And so if we consider A to be the endpoint of that particular interval, as long as you're on that interval, the function values are getting bigger. But if we consider the interval that starts at A and goes to the right, the function values are getting smaller. And so is the function increasing or decreasing at A? Well, the answer is yes. And it just depends on which side of A you're talking about. That's actually going to be characteristic of having a local maximum or local minimum, which we're about to see. Next, we're going to look at local or relative maximum and local or relative minimum. These are referred to as local extrema. And in fact, if you have more than one, the plural of maximum is maxima, and the plural of minimum is minima. Yeah, I'm getting a lot of mileage out of this graph, aren't I? Again, intuitively, it'll make sense that, or it should make sense, a local maximum is like king of his own hill. So at A, I have a local maximum. There's a peak there. Let me get that dot there. At E, I have a local maximum. There's a peak there. And then I have a local minimum at B and a local minimum at F. Intuitively, should make sense. Definitions. A function f has a local or relative maximum at A if f of A is bigger than f of x for all the x that are near it. It says for all x in an open interval containing A. In other words, if I go back to this graph here, if there's a little neighborhood around A such that f of A is bigger than everything else in that neighborhood, then I have a local maximum at A. The local maximum itself is f of A. In other words, it's the function value. How big is the y value? We have an analogous definition for a local minimum. A function f has a local or relative minimum at B if f of B is, oops, that should say less than. Let me fix that. If f of B is less than f of x for all x in an open interval containing B. In other words, I have a neighborhood around B in which f of B is the smallest value. Now notice that if we go to the left of A, the function has an arrow going down to negative infinity, and we might say, wait a minute, it's smaller over here, the y value, than it is at B. Yeah, but this definition is about an open interval containing B. So if I'm near B, then I found a little minimum there, and that's what's referred to as the local minimum. We aren't looking for the king of all the hills, just the king of that hill, or in this case, the king of the valley, I suppose. Of course, we have a couple of other places where we had a max and a min, but we'll actually look at that in the next slide. In each case, notice that the y value indicates where the extremum is. but the actual extreme value itself is the y value. Okay, so it tends to be a point of confusion in my experience where folks aren't sure how to answer stuff. On the next slide I have, guess what, the same picture. So you're going to be asked things like where is a local maximum and what is the maximum value? And this slide here is designed to help you answer those questions. If we have a function named, say, f, then we consider the point at a. It has coordinates of a, f of a. And as we said on the previous slide here, the first coordinate, the x coordinate, tells me where the value is. The second coordinate, or the y coordinate, tells me what the value is. In other words, when we're concerned with what the actual maximum is, what I want to know is what's the number on the y-axis. So to answer these questions, we're going to say something like there is a local maximum at x equals a, and then the maximum value is f of a. Notice there's another local maximum at x equals e, and so we would similarly say there's a local maximum at x equals e, and that maximum value is f of e. Likewise, we have local minima at x equals b and at x equals f, and so we would write statements like there's a local minimum at x equals b, that minimum value is f of b, and finally there's a local minimum at f, that minimum value being f of f. Guess I should have seen that coming when I picked these letters. In any case, identify the local extrema and where they occur. This would be a sufficient answer for that.